Close your eyes for a moment and imagine floating in the infinite darkness of space. Around you, billions of stars twinkle like distant diamonds scattered across black velvet. You drift past galaxies, spiral arms of light spinning slowly through the cosmic dance that has played out for billions of years. But now imagine discovering something that changes everything, something that shouldn't be there, something that violates every law we thought governed the universe. Not a star, not a galaxy, not even a cluster of galaxies. A wall, a cosmic wall of unimaginable proportions, stretching across the very fabric of reality itself. A structure so impossibly vast that according to everything we know about physics and cosmology, it simply cannot exist. And yet, there it is. Astronomers have given it a name that sounds almost mythical: the Hercules-Corona Borealis Great Wall. But don't let the scientific terminology fool you. This is not just another celestial object to be cataloged and filed away. This is a cosmic impossibility made manifest. Picture this: 10 billion light years across. 10 billion light years. If you could somehow travel at the speed of light, the fastest speed possible in our universe, it would take you over 10 billion years to cross this structure. That's longer than twice the age of our entire solar system. Longer than the time it took for the first simple life forms to evolve into the complex beings we are today. It is a wall made of galaxies. Billions upon billions of galaxies, each containing hundreds of billions of stars. Each of those stars potentially warming planets we'll never see, all arranged in a pattern that defies comprehension. But here's what makes this discovery so unsettling, so fundamentally disturbing to our understanding of reality. According to our best theories, according to the Big Bang model that explains the birth of our universe, according to cosmic inflation theory that describes how space itself expanded in the earliest moments of time, according to computer simulations that model the evolution of cosmic structure over billions of years, structures like this are impossible. The mathematics are clear. The physics are unambiguous. Nothing in our universe should be larger than 1.2 billion light-years across. That's the theoretical upper limit, written into the very equations that govern reality. A cosmic speed limit for the size of structures. And yet here we have something nearly 10 times larger than that limit. 10 times larger than what should be possible. So we're faced with a choice. Either our instruments are lying to us, our observations are somehow fundamentally flawed, or everything we thought we knew about the large-scale structure of the universe is wrong. Could this wall be an illusion? A cosmic mirage created by the tricks of light and distance? Or could it be evidence of something far stranger? Something that hints at hidden dimensions folded beneath the surface of reality? Forces beyond our current comprehension? Perhaps even other universes? This is the story of the cosmic wall that shouldn't exist, and it's a story that may rewrite everything we think we know about the universe and our place within it. To truly understand why this discovery has shaken the foundations of cosmology, we need to take a step back. We need to understand how humanity learned to map the cosmos itself. For thousands of years, when our ancestors looked up at the night sky, they saw chaos. Stars scattered randomly across the heavens with no apparent pattern or purpose. Ancient civilizations created constellations not because the stars were actually connected, but because the human mind desperately seeks patterns even where none exist. Then, as our telescopes grew more powerful, as we peered deeper into the cosmic darkness, we began to realize something extraordinary. The universe is not random at all. Stars cluster together to form galaxies. Galaxies group together into what we call galaxy clusters. These clusters form even larger structures called superclusters, and these superclusters weave together into vast filaments of matter, creating what astronomers now call the cosmic web. Imagine, if you will, a three-dimensional spider web spanning the entire observable universe. Threads of galaxies connected by invisible filaments of dark matter, creating a structure that resembles the neural networks in your brain, or the intricate patterns of blood vessels in your body, or the root system of a vast cosmic tree. This cosmic web is not poetry, it's not metaphor, it's real. We've measured it, we've mapped it. Surveys like the Sloan Digital Sky Survey have photographed millions of galaxies, measured their distances, and plotted their positions in three-dimensional space. What they revealed was breathtaking. Instead of cosmic chaos, there was cosmic order, structure on a scale that would have been unimaginable to previous generations. And yet this order had rules, laws, limits. Using Einstein's equations of general relativity, using our understanding of cosmic inflation, using massive compute, or simulations that model the evolution of structure over billions of years, cosmologists determined that there should be an upper limit to how large these structures can grow. That limit is approximately 1.2 billion light-years. Beyond that scale, the universe should appear smooth, homogeneous, like cream stirred into coffee, where all the swirls and patterns eventually blend into a uniform mixture. But in 2013, something changed everything. A group of astronomers were studying gamma-ray bursts. These are some of the most violent, energetic events in the universe. They occur when massive stars collapse into black holes, releasing more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. These bursts are so bright they can be seen from billions of light-years away, and because they mark the deaths of massive stars, they also mark the locations of galaxies. They're like cosmic lighthouses scattered across the universe. But as the astronomers cataloged these bursts, as they plotted their positions on their cosmic map, they noticed something strange, something that shouldn't have been there. The bursts weren't scattered randomly, they were clustering, forming a pattern on an almost incomprehensible scale, a pattern spanning 10 billion light-years. Not just a filament, not just a supercluster, an entire wall of galaxies. A cosmic structure so vast that if you could somehow see it in its entirety, it would stretch across a significant fraction of the observable universe itself. They called it the Hercules-Corona Borealis Great Wall. And if it's real, if it's truly what it appears to be, then it's not just the largest structure ever discovered. It's an impossibility, a violation of the very principles that govern cosmic evolution. And that raises a question that goes to the heart of everything we think we know about reality. Is our cosmic map incomplete, or is the universe itself far stranger than our equations can possibly describe? The discovery of this cosmic wall wasn't the result of accident or luck. It was the result of patient, methodical detective work, the kind of scientific investigation that slowly pieces together clues scattered across billions of years and trillions of miles. The story begins with gamma-ray bursts. To understand their importance, you need to understand what they are. The death screams of the universe's most massive stars. Imagine a star so massive that our own sun would seem like a grain of sand beside a mountain. When such a star runs out of fuel, it doesn't simply fade away like smaller stars. Instead, its core collapses in a fraction of a second, forming a black hole and unleashing a torrent of energy that can outshine an entire galaxy. These gamma-ray bursts are so incredibly bright that we can detect them from the very edge of the observable universe. They serve as cosmic beacons, marking the locations where massive stars once lived and died. And since massive stars only form in galaxies rich with gas and dust, these bursts essentially map the distribution of matter across the cosmos. For decades, astronomers have been cataloging these bursts, recording their positions, measuring their distances, building up a three-dimensional map of where they occur. It's painstaking work, requiring years of observations and careful analysis. But as the data accumulated, something began to emerge from the numbers. Something unexpected. Instead of being randomly scattered across the sky, the way you might expect if the universe were truly uniform, the gamma-ray bursts seemed to be aligned, clustered, organized into a pattern that spanned an enormous region of space. When the astronomers completed their analysis, they found themselves staring at something that shouldn't exist, a structure over 10 billion light-years in length. To give you a sense of that scale, the observable universe itself is about 93 billion light-years across in total. This wall, then, represents more than 1/10 of everything we can possibly see. It's like discovering that 1/10 of all reality is organized into a single massive structure. Of course, the scientific community's first reaction was skepticism, and rightfully so. Extraordinary claims require extraordinary evidence. Could this be a statistical fluke? A trick of random chance that made unrelated objects appear connected? Could it be sampling bias? Perhaps gamma-ray bursts aren't evenly distributed throughout the universe for reasons we don't understand. Could it be an observational error? Maybe our instruments were systematically miscounting or mismeasuring the positions of these distant events. But as additional data came in, as other research teams independently analyzed the same observations, as different statistical methods were applied to test the robustness of the result, the clustering refused to go away. Study after study continued to suggest that the pattern was real, that somewhere out there in the cosmos, across a distance so vast it challenges human comprehension, matter has organized itself into a wall of galaxies. If this is true, if the Hercules-Corona Borealis Great Wall actually exists, then it represents more than just a record-breaking discovery. It represents a fundamental challenge to our understanding of how the universe works. Because if such a structure can exist, then our models of cosmic evolution, our theories of how matter clumps together under the influence of gravity, our understanding of the limits imposed by the expansion of space itself, all of it may be incomplete. And that raises even deeper questions. What kind of forces could create such a structure? Gravity, too weak on such enormous scales to organize matter so precisely. Dark matter? It clumps, yes, but computer simulations suggest it can't create structures this large. The expansion of the universe? That should smooth things out, not create massive walls. Could it be that we're missing something fundamental about how the universe operates? Some force or phenomenon that our current physics simply doesn't account for? Or could this wall be something else entirely? Not just a collection of galaxies, but a boundary, a border, a cosmic landmark pointing towards something even more extraordinary? Something that might redefine our very understanding of what reality is and what lies beyond the edges of the universe we thought we knew. The existence of this cosmic wall forces us to confront one of the most fundamental assumptions in all of cosmology. An assumption so basic, so taken for granted that questioning it feels almost like questioning whether the sky is blue or whether water is wet. It's called the cosmological principle. And on the surface, it seems almost embarrassingly simple. The universe, when viewed on the largest possible scales, should look the same no matter where you are or which direction you look. Think of it this way. If you could somehow step outside our galaxy, outside our local group of galaxies, outside our supercluster, if you could view the universe from a truly cosmic perspective, then no matter where you positioned yourself, the view should be essentially identical. The same density of matter, the same types of structures, the same overall patterns. This principle isn't just an academic curiosity. It's the foundation upon which virtually all of modern cosmology is built. The Big Bang Theory depends on it. Our understanding of the cosmic microwave background radiation depends on it. Our calculations of the age and size of the universe depend on it. But the Hercules-Corona Borealis Great Wall, if it's real, shatters this principle entirely. Because if such a massive structure exists, then the universe is not uniform. It's not the same in all directions. Instead, it's lumpy, asymmetrical, there are regions of enormous density separated by vast cosmic voids. Imagine baking a loaf of bread, but something goes wrong with the oven. Some parts of the loaf rise properly and become light and fluffy. Other parts remain dense and heavy. Still other parts collapse entirely, leaving hollow spaces. The cosmological principle says the universe should be like a perfectly baked loaf, uniform throughout. But the wall suggests it might be more like that flawed loaf, with regions of vastly different properties. But there's an even more troubling issue lurking beneath the surface. The wall doesn't just violate the cosmological principle, it also violates our understanding of cosmic inflation. Cosmic inflation is the theory that explains how the universe expanded from a subatomic speck to its current vast size in the first tiny fraction of a second after the Big Bang. During this period, space itself expanded faster than the speed of light, stretching and smoothing out any irregularities that might have existed in the primordial universe. Think of inflation like taking a wrinkled balloon and inflating it to enormous size. As it expands, the wrinkles get stretched out until the surface appears perfectly smooth. Similarly, inflation should have smoothed out the early universe, ensuring that no region could be dramatically denser than any other region. The mathematics of inflation set clear limits on how large structures can grow. Those limits suggest that nothing should exceed about 1.2 billion light-years across. Beyond that scale, the smoothing effects of inflation should have prevented any significant clustering of matter. So we're faced with a profound dilemma. Either the wall is somehow an illusion, a misinterpretation of our observations, or our understanding of inflation itself is fundamentally incomplete. And if inflation is incomplete, if our models of the early universe are wrong, then what does that mean for everything else we think we know? What mechanism could create structures larger than inflation should allow? Could dark matter behave in ways we haven't yet discovered, weaving cosmic tapestries on unimaginable scales? Could dark energy, the mysterious force driving the acceleration of the universe, be uneven in ways that sculpt massive walls of galaxies? Or could the answer lie in something even more exotic? Forces that operate beyond our current understanding of physics? Interactions with dimensions we can't directly observe? Perhaps even echoes from other universes entirely? The truth is we don't know, and that uncertainty, that gap in our knowledge, represents one of the most exciting and terrifying frontiers in all of science. Because if we're wrong about something as fundamental as the large-scale structure of the universe, what else might we be wrong about? What other cosmic surprises might be waiting for us as we peer deeper into the darkness? And perhaps most unsettling of all, what if this wall is not just a structure, but a boundary? A border marking the edge of something larger than the universe itself. To understand where this impossible wall might have come from, some scientists are looking not forward into the future, but backward, deep into the ancient past. Back to a time when the universe was young and malleable, when the very foundations of reality were still taking shape. Imagine traveling back in time, not years or centuries, but billions of years, back to when the universe was only 380,000 years old, a cosmic infant compared to its current age of nearly 14 billion years. At that moment in cosmic history, the universe cooled enough for atoms to form for the first time. Before this moment, space was filled with a hot, glowing plasma that light could not penetrate. But suddenly, as atoms formed, the universe became transparent. Light could finally travel freely through space. That light is still traveling today. We call it the cosmic microwave background radiation, or CMB. It's like a baby picture of the universe, showing us what conditions were like in those earliest moments. When we map this ancient light across the entire sky, we see tiny variations in temperature, regions that were slightly warmer or slightly cooler than average. These variations are incredibly small, We're talking about differences of just a few millionths of a degree. But those tiny variations were the seeds of everything we see today. Regions that were slightly denser than average eventually attracted more matter through gravity, growing into the first stars, the first galaxies, and eventually the cosmic web itself. Here's the problem. When we look at the cosmic microwave background, we see small-scale variations, ripples that could grow into galaxies and galaxy clusters. But we don't see anything that could account for a structure as massive as the Hercules-Corona Borealis Great Wall. The variations we observe in the CMB are far too small to produce such an enormous structure, the rough normal gravitational growth. It's like looking at tiny ripples on a pond and trying to explain how they could grow into a tidal wave. So where did this wall come from? Could it be the result of some unknown process in the early universe? Some exotic physics that operated during the first moments after the Big Bang? Or could it be something even stranger? Could it be evidence that our universe is not alone? Some theories suggest that our universe is just one bubble in an infinite sea of universes. Each bubble universe expands and evolves independently, but occasionally, very rarely, two bubbles might brush against each other. Imagine two soap bubbles floating through the air, each containing its own universe. What happens when they touch? The collision would send shock waves through both universes, creating patterns and structures that could never form naturally within a single bubble. Could the Hercules-Corona Borealis Great Wall be exactly that? A scar? A cosmic battle wound left behind by a collision between our universe and another universe in the distant past? If this is true, then the wall is not just a collection of galaxies. It's evidence. Physical proof that reality extends far beyond the boundaries of our own cosmic bubble. That somewhere out there, other universes exist, each with their own laws of physics, their own stars and planets, their own possibilities for life and consciousness. Of course, this is speculation. The collision hypothesis remains unproven, perhaps unprovable with our current technology. But speculation has always been the bridge between what we know and what we might discover. Every great scientific breakthrough began with someone asking, what if? What if our universe bears the scars of ancient cosmic collisions? What if the wall is a window into the multiverse itself? And if that's true, what other evidence might be hidden in the cosmic background radiation? What other scars might we discover as our instruments become more sensitive? What other universes might have left their mark on our reality? But there's another possibility. Another set of cosmic actors that might be responsible for sculpting this impossible wall. Forces that make up the vast majority of our universe, yet remain almost completely mysterious to us. We call them dark matter and dark energy. And despite their ominous names, they're not evil or supernatural. They're called dark simply because they don't emit, absorb, or reflect light. They're invisible to our telescopes, detectable only through their gravitational effects on the matter we can see. But here's what makes them so important. Together, dark matter and dark energy make up about 95% of everything that exists in our universe. That means everything we can see, every star, every planet, every galaxy, every human being represents less than 5% of reality. We are literally living in a universe dominated by invisible forces we barely understand. Dark matter acts like cosmic scaffolding. It forms vast, invisible webs throughout space. And normal matter, the stuff we're made of, simply flows along these dark matter highways, clustering where the dark matter is densest. Computer simulations show us how dark matter should behave. Under the influence of gravity, it should clump together, forming structures of increasing size over cosmic time. But these simulations also suggest limits. Dark matter structures should not be able to organize on the scale of the Hercules-Corona Borealis Great Wall. But what if we're wrong? What if dark matter doesn't behave exactly the way our simulations predict? What if dark matter particles can interact with each other in ways we haven't yet discovered? What if they can form incredibly dense filaments that act like cosmic highways, channeling normal matter across billions of light years? Imagine a dark matter structure so massive, so precisely organized, that galaxies simply flow along it like cars on a highway. From our perspective, we would see a wall of galaxies, but the real structure, the invisible architecture holding it all together, would be made of dark matter. But dark energy presents an even more intriguing possibility. This mysterious force is driving the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. We've always assumed that dark energy is uniform throughout space, the same strength, the same properties, everywhere in the universe. But what if that assumption is wrong? What if dark energy varies from place to place? What if it's stronger in some regions and weaker in others? If dark energy is uneven, then space itself would expand at different rates in different regions. Areas with weaker dark energy would expand more slowly, allowing matter to clump together more easily. Areas with stronger dark energy would expand rapidly, creating vast voids. Over billions of years, this uneven expansion could sculpt the universe like a cosmic artist, creating walls of galaxies in regions where dark energy happens to be weaker, separated by enormous voids where dark energy dominates. But if this is true, if dark energy is not uniform throughout space, then the implications go far beyond explaining a single cosmic structure. It would mean that the fate of the universe itself is uncertain. Some regions might continue accelerating, expanding forever until galaxies become isolated, islands in an increasingly empty cosmos. Other regions might slow their expansion, perhaps even reversing it, collapsing back into a cosmic crunch. The Hercules-Corona Borealis Great Wall might not just be a record of the past, it might be a preview of the future, a glimpse of how dark energy could fragment the universe into distinct regions, each following its own cosmic destiny. In such a universe, the wall wouldn't just be a structure, it would be a border, a boundary between regions of space that are literally evolving in different directions. And if we're living in such a universe, what does that mean for us? For our galaxy? For our cosmic neighborhood? Are we on one side of a cosmic divide or the other? Of course, there's another possibility we must consider, one that's perhaps less exciting but no less important to acknowledge. What if the Hercules-Corona Borealis Great Wall doesn't actually exist? What if this cosmic impossibility is nothing more than a very convincing illusion, a trick played on us by the vast distances and complex geometry of the universe itself? After all, the cosmos is an enormous place, filled with countless galaxies and structures. In such a vast arena, patterns will appear by pure chance, clusters that seem meaningful but are actually just random coincidences. Think about the constellations in our night sky. From Earth, the stars in Orion appear to form the shape of a hunter, connected by invisible lines, but this is purely an accident of perspective. The stars in Orion are actually at vastly different distances from us, scattered throughout three-dimensional space with no real connection to each other. Could the wall be a similar illusion? Could gamma-ray bursts that appear to be aligned actually be scattered randomly through space, only seeming to form a pattern because of the particular angle from which we observe them? There are other concerns as well. Gamma-ray bursts are complex phenomena, and we're still learning about how they work. What if they're not the reliable tracers of galaxy distribution that we assume them to be? What if certain types of galaxies are more likely to produce gamma-ray bursts than others? What if environmental factors affect the probability of these explosions in ways we don't yet understand? What if our instruments are better at detecting bursts from certain regions of space? What if atmospheric interference or instrumental limitations are creating apparent patterns where none actually exist? These are legitimate scientific concerns. In science, extraordinary claims require extraordinary evidence, and a Cosmic structure that violates the fundamental principles of cosmology is about as extraordinary as claims get. The scientific community continues to investigate these possibilities. Researchers are developing new statistical methods to test whether the observed clustering could be due to chance. They're studying the properties of gamma-ray bursts more carefully to understand whether they're reliable cosmic tracers. They're looking for independent evidence that could either confirm or refute the wall's existence. And yet, as more data accumulates, as different research teams apply different analytical methods, as new observations are made, the pattern refuses to go away. Multiple independent studies have now examined the distribution of gamma-ray bursts, and most continue to find evidence for large-scale clustering. The statistical significance of the pattern has grown stronger over time, not weaker. Moreover, astronomers have begun to find supporting evidence from other types of observations. Studies of galaxy distributions, analyses of the cosmic microwave background, and large-scale structure surveys all hint at irregularities on scales that shouldn't exist according to standard cosmological models. While healthy skepticism remains, a growing number of researchers are becoming convinced that something unusual is indeed happening on the largest scales of the universe. Whether it's the specific wall identified through gamma-ray bursts or some other large-scale anomaly, the evidence suggests that our understanding of cosmic structure may be incomplete. And perhaps that's as it should be. Science advances not by confirming what we already believe, but by discovering phenomena that challenge our preconceptions. Whether the wall is real or illusory, the very process of investigating it has already expanded our vision of what the universe might be. It has forced us to question assumptions we didn't even know we were making. In a sense, the wall has already achieved something profound, regardless of whether it physically exists. It has reminded us that the universe is under no obligation to conform to our expectations. That reality may be stranger, more complex, and more wonderful than our current theories can capture. But if the wall is real, if it truly exists as more than just an observational artifact, then we must ask the ultimate question: what does it mean? Not just as a scientific discovery, but as a revelation about the nature of reality itself. Let us dare to venture into the realm of the truly speculative. Let us ask the questions that push the boundaries of not just cosmology, but of our very conception of what reality might be. What if the Hercules-Corona Borealis Great Wall is not just a collection of galaxies? What if it's something far more fundamental? Something that reveals hidden aspects of the universe that we've never even imagined. Consider this possibility. What if our universe, everything we can see and touch and measure, is actually just a three-dimensional slice of a much larger, higher-dimensional reality? Some of the most advanced theories in physics suggest that we might be living on what scientists call a brane, short for membrane. Imagine a flat sheet of paper floating in a three-dimensional room. From the perspective of a two-dimensional being living on that paper, the room itself would be invisible and incomprehensible. Similarly, our three-dimensional universe might be like that sheet of paper, floating in a space of 4, 5, or even 11 dimensions. We can't perceive these extra dimensions directly, but they might still affect what we observe. What if the cosmic wall represents a fold or crease in our three-dimensional brain, a place where our universe bends through higher dimensional space, causing matter to accumulate like dust gathering in the creases of a folded cloth? If this is true, then the wall isn't just large, it's a window into the architecture of higher dimensional space itself, a glimpse of the cosmic machinery that operates beyond our three-dimensional perception. But let's consider an even more radical possibility, one that has gained serious attention from physicists and philosophers in recent years. What if our entire universe, including the wall, is a simulation, an incredibly sophisticated computer program running on some unimaginably advanced computational substrate? Even the most advanced simulations have limitations. They have finite memory, finite processing power, finite resolution, and these limitations sometimes manifest as glitches, boundaries, or repeating patterns in the simulated environment. Could the Hercules-Corona Borealis Great Wall be exactly that, a computational artifact? A place where the simulation reaches its limits, where the code that generates our reality shows its underlying structure. In a simulated universe, you might expect to find certain telltale signs, regular patterns that repeat across vast distances, structures that exist at the maximum scales the simulation can handle, boundaries that seem artificial rather than natural. The wall, spanning such an enormous fraction of the observable universe, existing right at the theoretical limits of what our cosmological models say should be possible, could it be the edge of the simulation itself? The place where the programmers of reality ran out of computational resources? Or consider this: what if the wall is not made of matter at all, but of information? Some physicists propose that at the deepest level, reality is not made of particles or waves or energy, but of information, bits of data that, when organized in certain ways, give rise to the illusion of physical matter and space-time. And if reality is fundamentally informational, then consciousness, awareness itself, might play a role in determining what exists and what doesn't. The act of observation might literally create reality, not just reveal it. Could the wall be a manifestation of some vast cosmic consciousness? A structure that exists because it is being observed, maintained by the collective awareness of countless intelligent beings throughout the universe? Perhaps every time we study the wall, every time we measure its properties and debate its existence, we are actually participating in its creation. Our consciousness, our attention, our scientific inquiry, perhaps these are not just studying reality but actively constructing it. Or what if the wall marks a boundary between different versions of reality itself? Different quantum branches of the universe, each following its own evolutionary path. In quantum mechanics, some interpretations suggest that every possible outcome of every quantum event actually occurs, but in separate, parallel universes. These parallel realities branch off from each other constantly, creating an infinite tree of possibilities. What if the wall represents a place where different quantum branches of reality intersect, a cosmic junction where multiple versions of the universe overlap, creating gravitational effects that draw matter together into this impossible structure? These ideas may sound like science fiction, and perhaps they are, but science fiction has a remarkable track record of becoming science fact, given enough time and investigation. The Big Bang was once considered absurd. Quantum mechanics was once thought impossible. Black holes were considered mathematical curiosities that couldn't possibly exist in nature. The wall forces us to expand our imagination, to consider possibilities that stretch the boundaries of current knowledge. Whether it's higher dimensions, simulation theory, consciousness-based reality, or quantum multiverse effects, the wall reminds us that the universe may be far stranger than we dare to imagine. And perhaps that's the wall's greatest gift to us. Not answers, but better questions. Not certainty, but wonder. Because ultimately, the wall is not just a cosmic structure, it's a mirror reflecting our deepest questions about the nature of existence itself. So where do we go from here? How do we move from speculation to understanding? How do we transform this cosmic mystery into cosmic knowledge? Around the world, astronomers are working to gather more data. New telescopes, more sensitive instruments, better analytical techniques, all focused on understanding whether the wall is real, and if so, what it might represent. The James Webb Space Telescope, with its unprecedented ability to peer deep into cosmic history, may provide crucial insights. Future gamma-ray observatories will catalog even more bursts with greater precision. Advanced computer simulations will test whether any known physics can account for such a structure. But perhaps most importantly, we're developing new ways of looking at the universe itself. Gravitational wave detectors might reveal hidden aspects of large-scale structure. Dark matter and dark energy surveys might uncover the invisible scaffolding that shapes cosmic architecture. This is not a mystery that any one nation or research team can solve alone. It requires the combined efforts of the global scientific community, sharing data, comparing results, challenging each other's conclusions, and it requires continued healthy skepticism, the willingness to question not just the wall's existence, but our methods of investigation, our assumptions about how the universe works, and our interpretation of the data we collect. But there's something else we must acknowledge. If the wall is real, truly real, then understanding it may require new physics, new theories that go beyond our current models of cosmology and particle physics. This wouldn't be unprecedented. The discovery of the accelerating expansion of the universe forced us to postulate dark energy. The observation of galaxy rotation curves led to the concept of dark matter. Sometimes the universe presents us with phenomena that can only be understood by expanding our theoretical framework. The wall may be forcing us toward another such expansion, toward new concepts, new mathematics, new ways of thinking about space, time, matter, and energy. And that's not something to fear, it's something to celebrate. Because each time we've been forced to expand our understanding, we've gained new insights, not just about the cosmos, but about our place within it. And so we return at last to where we began. To the Hercules-Corona Borealis Great Wall, stretching across 10 billion light-years of space, challenging everything we thought we knew about the universe. We've explored the possibilities, cosmic mirage or fundamental reality, statistical fluke or revolutionary discovery, evidence of dark forces, higher dimensions, simulation boundaries, or quantum intersections. But perhaps the most remarkable thing about this wall is not what it might be, but what it has already accomplished. Without providing a single definitive answer, it has forced us to ask better questions. Questions about the nature of space and time, about the limits of scientific knowledge, about the role of consciousness in shaping reality, about whether our universe is alone or part of something infinitely larger. In challenging the cosmological principle, the wall has challenged us to think more deeply about uniformity and structure. In violating the theoretical limits of cosmic inflation, it has pushed us to reconsider our models of the early universe. But on a more personal level, the wall reminds us of something profoundly important about the human condition. We are small beings in a vast cosmos, trying to understand something immeasurably larger than ourselves. From our tiny planet, orbiting an ordinary star in a typical galaxy, in a universe that may itself be just one of countless universes, we dare to map the cosmos. We dare to ask whether reality has boundaries, whether existence has patterns, whether the universe makes sense. And perhaps that's the most miraculous thing of all. Not the wall itself, but our ability to perceive it, our willingness to question it, our determination to understand it, even when understanding seems impossible. The wall stands as a symbol of the eternal dialogue between human curiosity and cosmic mystery. Every answer we discover reveals new questions. Every boundary we cross shows us new horizons. Whether the Hercules-Corona Borealis Great Wall is ultimately proven real or revealed as illusion, it has already served its purpose. It has reminded us that the universe is under no obligation to conform to our expectations. It has shown us that mystery is not something to be eliminated, but something to be embraced. That the unknown is not an enemy to be conquered, but a frontier to be explored. And it has demonstrated that science, at its best, is not about collecting facts, but about expanding wonder. Not about final answers, but about better questions. Not about certainty, but about the courage to remain uncertain while continuing to search. So as we gaze out into the cosmic darkness, knowing that somewhere in that vast expanse there may exist a wall of galaxies spanning a significant fraction of everything we can possibly observe. Let us remember that we are part of this story. We are not separate from the universe we study. We are expressions of it, arrangements of cosmic matter that have become aware of themselves and curious about their origins. And perhaps that's the wall's ultimate message, not a lesson about cosmology or physics, but a reminder about consciousness itself, about the miracle of awareness arising from matter, about intelligence questioning its own existence. In a universe of dark matter and dark energy, of cosmic walls and quantum uncertainties, perhaps the greatest mystery of all is not what lies at the edge of reality, but what lies at the center of our own awareness, the consciousness that allows us to perceive walls spanning billions of light years, the curiosity that drives us to question the nature of existence itself. The Hercules-Corona Borealis Great Wall may or may not exist, but our wonder at its possibility, our determination to understand it, our willingness to be amazed by the cosmos, that is real, that is undeniable, and that perhaps is the most profound cosmic structure of all. The wall that shouldn't exist has shown us something that undeniably does, the infinite capacity of consciousness to reach toward the infinite mystery of existence itself. And the search, the eternal, beautiful search for understanding, continues.